Hello everyone, I'm Eija Tanskanen from Aalto University, and this talk will give you space weather and space climate angle to the interplanetary CubeSat mission design. So there are two main purposes in this talk, and one is to better understand how the variable space weather conditions affect the CubeSats. And the other one is how the CubeSats, interplanetary CubeSat fleet could be used for better space weather monitoring and prediction. So this is first to give an overview of the solar activity and geomagnetic activity. In this talk I will concentrate on magnetic fluctuations and how do they affect, how do they vary in different time scales and how do they affect to the infrastructure. So with gray I will show the sunspot number, which will show you the different solar cycles from 1844 onwards, and by red it is shown the geomagnetic activity. And typically geomagnetic activity follows solar activity, but with 2 to 3 years lag. And now we want to understand during this talk how solar activity is driving geomagnetic activity and how does magnetic activity vary in solar wind to make the coupling between Sun and Earth in different time scales and spatial scales possible. So on the left-hand side, I will show you three pictures of the Sun. And then on the right-hand side, there are three different perspectives to the auroral substorms, which is one of the main features I will study here today. So this picture will show you how auroral substorm activity vary over different time scales of years and seasons. So in x-axis I will show you years for the solar cycle 23, and in y-axis you will see the seasons, months. So typically you may have learned that the largest geomagnetic activity occurs in spring and fall. That is pretty much true in multi-year averages, and you can also see that in this picture. But there are also other variability in different time scales, and you may see the largest activity occurring during winter 2003 and 4 and 5, that red area there in the lower part of the picture. So it means that geomagnetic activity doesn't always vary so that there are double peak spring and fall activity, but it depends largely on the solar activity. So during those years when we see a lot of red, we will have a huge coronal holes, elongated coronal holes in solar surface. So those are generating this very strong geomagnetic activity. And it is much better known that during solar minimum we have very little geomagnetic activity, and that is shown by blue color there. Also during summertime we have least. Then we want to understand that what is actually driving geomagnetic activity. It is driven by structures in solar wind called high-speed streams. It is known from 1960s that interplanetary magnetic field is important for allowing solar wind plasma to enter into the magnetosphere. However, it hasn't been known for a very long time how important the solar wind speed is originating from the solar coronal holes. But that you can see from this picture. In the upper right panel, you will see how closely auroral substorm activity shown by black curve follows the red curve. And then in the lower left corner, you will see that how well geomagnetic storms at equator follow coronal mass ejections. So that is the main result from this. And later on, I will show you what is important in high-speed streams. What should we be concerned and what should we learn better? It is the highly variable magnetic field fluctuations, Alfvénic fluctuations. So this is one example on the IMFBC variability. Interplanetary magnetic field varies in many different time scales from seconds and minutes to years and solar cycles. And this is the variability within few hours. So typically, it is very well known that when the IMFBC component is opposite to the terrestrial magnetic field, then we need to be concerned within magnetosphere. Then we will get new fresh plasma inside magnetospheres, Earth and other planets as well. So typically within those few hours when we see southward, we need to be worried about space weather effects on ground. But we have also variability in different time scales. And it has been found quite recently that the source of those fluctuations is actually coronal holes. It is both active regions, so sunspots, and coronal holes. Every now and then solar coronal holes are very small and close to the polar regions. And sometimes they are large, like in the southern hemisphere, they're in a pink plot, pink image. But at times they are very elongated, like in the northern hemisphere of the pink plot. And that's when we get most dangerous magnetic field fluctuations. And those are the times that we need to follow space weather very closely. Then what also matters is the magnetic complexity structure of the active regions, which is shown on the left-hand side. At times we have huge active regions at the solar surface, larger than Jupiter, what you will see there as well, for comparison. So sometimes you can imagine how complex and complicated the magnetic structure is in those huge structures. And with the very good images from SDO, SOHO, and other spacecraft, we have been able to better understand how this complex magnetic field affects to us and our infra in solar wind and on ground. So this is what we have primarily studied when using Hale classification, beta gammas and beta gamma deltas. So when we have not only bipolar magnetic field, but much more complicated than that. So this is a picture of the solar wind data itself. This is the solar wind speed from Sun towards the Earth. And it is quite clear that we have 27 days periodicity. And that's because of those huge active regions that we will see every 27 days when Sun rotates. So in 2002 we start to see effects of those in every 27 days, and in 2003 we have it in every rotation. And the power spectra on the right-hand side, you will also see the 27-day periodicity. It is not there every year. For example, in 2008 we won't see it. It's there only now and then, so we need to be careful when planning different missions that what is the solar cycle phase when we are launching that mission. So in different solar cycle phases we have different space weather conditions, and during some times they are very dangerous, hazardous, but during other times we are more safe. This is my one slide with equations. So this is the measure what we have used for the solar wind magnetic fluctuations. So we compute the solar wind Alfvénicity based on the normalized cross helicity sigma c. And that takes into account the magnetic field fluctuations and velocity field fluctuations. And whenever they are at the same phase, so that they are powering each other's, then we will get the magnetic signatures from the Sun to the Earth. If they are cancelling each other's, then we will lose the signal when it's transferred from the Sun to the Earth. So the requirement to get the magnetic signature from the Sun to the Earth is that those fluctuations are not cancelling each other's. That's the main point. And from the figure you will see that during early declining solar cycle phase, we will have most of those Alfvénic fluctuations when they have a lot of power to come from the Sun to the Earth. But during solar minimum, we have much less of those. And what you can see from this is that during early declining phase in 2003, more than half of the time we have those fluctuations. But during solar minimum, less than a few % of the time we have those. So that is the information that you need to take into account when planning the schedule for the mission. And then another picture about the origin of the Alfvénic fluctuation, which is shown by gray in the left-hand side. So the source of the Alfvénic waves is the borders of the coronal holes in the solar surface. So how could we study these fluctuations better? So far we have had quite nice interplanetary missions with magnetic field and velocity plasma instruments on board, but we don't have had them very many at the same time there. So we have been able to compute very simple things so far, but with such fleet, with several CubeSats, we would be really able to better understand the complex structure of the solar winds. And this is an example showing 4 spacecraft in the solar wind simultaneously, A, geotail and wind. And we will have such a configuration very rarely. So it's only very rarely when we can get data simultaneously from 4 different interplanetary missions. But what you can see from this event, one single event, is that how variable interplanetary magnetic field is. So it very much depends on the location of the spacecraft that what we will see. And it is quite crucial to understand also the spatial structure of the solar wind. Not just by using one spacecraft, but using as many as possible. And CubeSats are really good, give really good opportunities for that. And this talk was mainly about science, but we also have started doing a little bit hardware design. And this is our first try. We have built a scientific quality magnetometer that will fly on board SQ2 in the near future. Actually, we could already use CubeSat altitude magnetometer data for scientific quality analysis, but it's very much more challenging because of the lacking calibration routines and all that. But building a scientific quality magnetometer and take it on board CubeSats, that would give to us really valuable information on space weather and space climate. Thank you.
Any questions? With regard to the magnet measurement, did you think about magnetic leanness of your CubeSat and how to achieve that?
Yes, I have analyzed the data from the CubeSat that hasn't had any plans for clean lines, and it seems to be possible to get a signal even for that with the afterward analysis. But what we are trying now with S2 is that we will put 6 cheap, not very well quality magnetometers in each side of the CubeSat to be able to better understand the internal magnetic field variability, and then put 1 high quality magnetometer inside. That we will use for scientific purposes.
Inside?
Yes, inside.
Sorry, why inside, not with a boom?
Well, it depends on the other payload. If that is possible, we would prefer that, but yes.
Hello. So, do you have any, or do you have any idea of the requirements? How many CubeSats you will need? What's the spatial distribution that you would like? How long would you like to make observations, etc.?
Even 2 would give more than what we have at the moment. And spatial resolution, it could be even those spacecraft where 1 Earth radio apart. So it can be like up to that, but we can also get very valuable information if they are closer or further out. So yes, there are lots of variability on that.
Any other questions? I'm going to thank our speaker again.